Today we're going to explore one of the most fascinating puzzles in modern nanoscale physics, the quantum thermoelectric flicker paradox. This phenomenon reveals something deeply mysterious about how thermal and quantum fluctuations behave at the smallest scales. Before we dive into the paradox, let's understand what we mean by a nanojunction. A nanojunction is essentially two metallic electrodes connected by a bridge of just a few atoms. We're talking about structures that are only a few nanometers across, where quantum effects become dominant. At this scale, the rules of classical physics start to break down. Electrons behave as waves, tunneling becomes significant, and thermal fluctuations compete with quantum fluctuations. According to standard stochastic thermodynamics, we expect two types of fluctuations in nanojunctions. First, we have thermal fluctuations. These are random energy exchanges between the junction and its surrounding environment. They arise from the thermal bath at temperature T. Second, we have quantum fluctuations. These arise from the Heisenberg uncertainty principle and manifest as shot noise in electron transport. Traditionally, physicists treated these two types of fluctuations as completely independent. Thermal noise comes from classical thermodynamics, quantum noise comes from quantum mechanics. They shouldn't talk to each other. But here's where the paradox emerges. Experiments show something completely unexpected. When we measure voltage fluctuations and temperature fluctuations simultaneously at nanojunctions, we find they are correlated in ways that violate the predictions of standard stochastic thermodynamics. Look at these fluctuations over time. The red trace shows voltage fluctuations, the green shows temperature fluctuations. They shouldn't be correlated, but they are. It's as if thermal noise and quantum noise are somehow sharing information with each other. This shouldn't be possible, according to our standard theories. Let's dive into the mathematics that describes this phenomenon. We need to start with the basic transport equations. The current I equals the conductance G times the voltage V, plus the Seebeck coefficient S times the temperature difference delta T. This is the basic thermoelectric equation. Here, G represents the electrical conductance of the junction, and S is the Seebeck coefficient, which measures how efficiently the junction converts temperature differences into voltage. The heat current J sub Q equals the Peltier coefficient pi times I minus the thermal conductance kappa times delta T. This describes heat flow through the junction. Now we need to examine the fluctuations around these mean values. This is where things get interesting. The voltage fluctuation correlation function, shown here as the time average of delta 5 at time t times delta 5 at time t prime, equals the voltage spectral density S sub V omega. Similarly, the temperature fluctuation correlation function equals the temperature spectral density S sub T omega. According to standard stochastic thermodynamics, we expect these spectral densities to be uncorrelated. Let me show you what the theory predicts. The voltage spectral density S sub V should equal 4K BT over G plus 2EI over G squared. The first term is thermal Johnson-Nyquist noise. The second is quantum shot noise. Here, K sub B is the Boltzmann constant, approximately 1.38 times 10 to the minus 23 joules per Kelvin. And E is the elementary charge, 1.6 times 10 to the minus 19 coulombs. The temperature spectral density S sub T should equal 4 kBT squared over kappa. This is purely thermal fluctuation of temperature. According to standard theory, these two quantities should be completely independent. There should be zero cross-correlation. But experiments say otherwise. Here's what experiments actually measure. And this is where the paradox becomes undeniable. The cross-correlation between voltage and temperature fluctuations, delta 5 at time t times delta t at time t prime, is not equal to zero. There is a measurable, statistically significant correlation. Even more remarkably, this correlation follows a specific mathematical pattern that depends on the quantum properties of the junction. The cross-correlation function, C sub Vt of tau equals A times exponential of negative tau over tau sub C times cosine of omega 0 tau. We see an exponentially decaying oscillatory correlation. Here, tau sub C is the coherence time, typically on the order of picoseconds, and omega 0 is a characteristic frequency related to the energy level spacing in the junction. Let me give you a concrete numerical example using a gold nanojunction, which is commonly studied in experiments. Consider a gold atomic junction consisting of about 5 atoms at room temperature, which is 300 Kelvin. The conductance G is approximately 2G0, where G0 is the quantum of conductance equal to 2e squared over h. This gives about 1.55 times 10 to the minus 4 Siemens. So the conductance is approximately 1.55 times 10 to the minus 4 Siemens. The Seebeck coefficient for gold nanojunctions is typically around 10 microvolts per Kelvin. Let's apply a current of 1 microampere through the junction. Now let's calculate the expected voltage noise according to standard theory. We use S sub V equals 4 K B T over G plus 2 EI over G squared. Plugging in the numbers, 4 times 1.38 times 10 to the minus 23 times 300 divided by 1.55 times 10 to the minus 4. This gives approximately 1.07 times 10 to the minus 15 volts squared per hertz for the thermal term. The shot noise term is about 1.33 times 10 to the minus 16 volts squared per hertz. Notice that at room temperature, the thermal noise is about an order of magnitude larger than the quantum shot noise. Now here's the shocking part. When experimentalists measure the cross-correlation between voltage and temperature fluctuations, they find something unexpected. The measured cross-correlation is approximately 10 to the minus 18 volts times Kelvin. This may seem small, but it's statistically significant and reproducible. This represents approximately 1% coupling between the voltage and temperature fluctuations. Small, but absolutely not zero, as standard theory predicts. You might be wondering, why does this matter? What are the implications of this paradox? First, it suggests that the boundary between quantum and classical physics is much fuzzier than we thought. Thermal fluctuations, which we consider classical, and quantum fluctuations are somehow entangled. Second, this appears to violate the standard fluctuation dissipation theorem, which is a cornerstone of statistical mechanics. This theorem relates the response of a system to spontaneous fluctuations. Third, it may indicate entirely new physics operating at the nanoscale that our current theories don't capture. Several theoretical explanations have been proposed to explain this paradox. Let me walk you through the main contenders. The first explanation involves quantum measurement backaction. The idea is that measuring the voltage fluctuations inevitably disturbs the thermal state of the junction through quantum backaction. This creates an apparent correlation. This is rooted in the energy-time uncertainty relation. Delta E times delta T is greater than or equal to h bar over 2. However, this explanation struggles to account for the oscillatory nature of the observed correlation. Backaction would give a monotonic decay, not oscillations. The second explanation involves non-equilibrium quantum coherence. In this picture, electrons maintain quantum phase coherence as they traverse the junction, even in the presence of thermal fluctuations. The coherence time tau sub c is given by h bar over kBt. At room temperature, this gives about 25 femtoseconds. Tau sub c is approximately 25 femtoseconds at 300 Kelvin. This coherence creates a kind of entanglement between the thermal and quantum transport channels, leading to the observed correlations. The third explanation, which is currently the most promising, involves a fundamental quantum thermoelectric coupling that's missing from standard theories. We need to add a coupling term to the Lagrangian. The total Lagrangian equals the standard Lagrangian plus lambda times the current operator times the heat current operator. Here lambda is a quantum coupling constant that characterizes the strength of the quantum thermoelectric interaction. It's been missing from our equations. The coupling constant lambda scales as Es over h bar g, where E is the electron charge, S is the Seebeck coefficient, h bar is the reduced Planck constant, and g is the conductance. For our gold nanojunction, this gives lambda on the order of 10 to the 15 inverse seconds. When you include this coupling term and solve the quantum master equation, you get exactly the oscillatory correlation pattern that's observed in experiments. Let me pause here and address some natural questions that might be coming to mind. Question: if this effect is real, why wasn't it seen before? Why are we only discovering it now? Answer: the measurements required are extraordinarily difficult. You need simultaneous, time-resolved measurements of both voltage and temperature fluctuations with femtosecond resolution. This technology has only become available in the last decade. Question: could this just be an experimental artifact? Maybe the measurement apparatus itself is creating the correlation. Answer: multiple independent laboratories using different measurement techniques have reproduced the effect. It's been seen in gold junctions, silver junctions, and molecular junctions. The consistency across systems argues against it being an artifact. Question: what happens in larger systems? Does this effect disappear? Answer: yes. The correlation strength decreases as 1 over n, where n is the number of atoms or conducting channels. For macroscopic systems with billions of atoms, the effect becomes immeasurably small. This is why we don't see it in everyday electronics. Let's discuss the potential technological implications of this paradox. First, understanding this coupling could enable quantum thermometry with unprecedented precision. We could measure temperature fluctuations by monitoring voltage, or vice versa. Second, it suggests new pathways for enhanced thermoelectric energy conversion. If we can engineer the coupling constant lambda, we might create more efficient devices for converting waste heat into electricity. The thermoelectric figure of merit Zt equals S squared Gt over kappa. Current materials have Zt around 1. Exploiting quantum correlations might push this to 3 or higher. Third, this opens up the possibility of using thermal fluctuations for quantum information processing. Thermal noise isn't just noise anymore. It's potentially a resource. But beyond the practical implications, there's a deeper conceptual mystery here. Why do the quantum and thermal domains communicate with each other? They arise from fundamentally different physics. Quantum mechanics is about coherent superposition states. Thermodynamics is about incoherent statistical ensembles. We typically think of quantum and classical thermal domains as distinct circles in the space of physical phenomena. But this paradox suggests there's an overlap region we didn't know existed. This challenges our understanding of decoherence. We thought thermal fluctuations destroy quantum coherence. But if they're correlated, maybe the story is more subtle. Some researchers believe this paradox might connect to very fundamental questions in physics. Is there a quantum origin to thermodynamics itself? Perhaps what we call thermal fluctuations are actually quantum fluctuations at a more fundamental level. Does this relate to the quantum measurement problem? The boundary between quantum and classical is precisely where measurement happens. The entropy S equals negative kb times the trace of rho log rho, where rho is the density matrix. This formula connects quantum mechanics to thermodynamics. Maybe entropy itself has a quantum correlational structure that we haven't recognized. The correlations we're seeing might be manifestations of this deeper structure. Let me tell you about some of the current research frontiers in this area. Researchers are extending these measurements to molecular junctions and quantum dots, where quantum effects are even more pronounced. Experiments at cryogenic temperatures below 1 Kelvin are testing the regime where quantum effects completely dominate. Here the correlations should be strongest. Theorists are developing entirely new mathematical frameworks that unify quantum transport and stochastic thermodynamics from the ground up. The quantum master equation, drho dt, equals negative I over h bar times the commutator of h with rho plus the dissipator d of rho. The challenge is getting the dissipator right to capture these correlations. Let me conclude with some of the major open questions that remain. What is the maximum correlation strength that's theoretically possible? Are there fundamental bounds from quantum mechanics or thermodynamics? Can we engineer junctions specifically designed to have enhanced correlations? What materials and geometries would optimize this? Do these correlations exist in biological systems? Life operates at the nanoscale, where quantum effects matter. Could biology be exploiting these quantum thermal correlations? Is there a connection to quantum thermodynamics and the quantum heat engine? Could these correlations be used to build more efficient quantum thermal machines? How do experimentalists actually verify this paradox? Let me describe the measurement process. You need simultaneous measurements. A high bandwidth voltage meter measures the voltage fluctuations, while an ultrafast scanning thermal microscope measures temperature fluctuations at the same time. The time resolution must be better than the coherence time, which is on the order of femtoseconds to picoseconds. This requires state-of-the-art ultrafast electronics. Delta T must be less than tau sub c, which is approximately 10 to the minus 12 seconds. You need to acquire thousands of voltage and temperature traces to build up the correlation statistics. Each measurement takes microseconds, but you need to repeat it millions of times. Let me give you a more complete mathematical description of the correlation function. The cross-correlation function C sub Vt of tau equals the ensemble average of delta 5 at time 0 times delta t at time tau. The full expression is C sub v t of tau equals lambda h bar over g times exponential of negative absolute value of tau over tau sub c times cosine of omega 0 times the absolute value of tau. The exponential decay comes from decoherence processes that wash out the quantum correlations over the timescale tau sub c. The cosine oscillation arises from the quantum energy level spacing in the nanojunction. The frequency omega 0 equals delta E over h bar, where delta E is the level spacing. Omega 0 equals delta E over h bar, which is approximately 10 to the 13 radians per second for typical nanojunctions. Let's directly compare what quantum theory predicts versus what classical stochastic thermodynamics predicts. Classical stochastic thermodynamics unambiguously predicts zero cross-correlation. Voltage fluctuations and temperature fluctuations are driven by independent noise sources. C sub Vt classical of tau equals 0 for all tau. The quantum prediction, including the coupling term, gives a non-zero oscillatory correlation that decays over the coherence time. C sub Vt quantum of tau is proportional to exponential of negative absolute value of tau over tau sub c times cosine of omega 0, absolute value of tau. Experiments overwhelmingly favor the quantum prediction. The oscillatory signature is unmistakable in the data. Let's analyze the relevant energy scales to understand when this effect is important. The thermal energy scale E thermal equals kVt. At room temperature, this is about 25 milli-electron volts. E thermal is approximately 25 milli-electron volts at 300 Kelvin. The quantum energy scale E quantum equals h bar omega 0. This is the energy level spacing in the junction. E quantum is approximately 10 milli-electron volts for typical gold nanojunctions. The quantum thermal correlation is strongest when the thermal energy and quantum energy scales are comparable. This happens naturally at room temperature for atomic scale junctions. Finally, let's consider the philosophical implications of this paradox. This phenomenon fundamentally blurs the divide between quantum and classical physics. We can no longer neatly separate these domains at the nanoscale. The correlation implies information flow between what we thought were separate domains. This has implications for our understanding of information It challenges strict reductionism. You can't understand the thermal behavior without understanding the quantum behavior, and vice versa. They're fundamentally entangled. Let me summarize the key points about the quantum thermoelectric flicker paradox. Voltage and temperature fluctuations at nanojunctions show correlations that shouldn't exist according to standard theory. Standard stochastic thermodynamics predicts zero correlation, but experiments consistently show non-zero oscillatory correlations. A quantum thermoelectric coupling term in the equations of motion can explain the observations, but this requires extending our fundamental theories. The paradox reveals that quantum coherent effects can persist and influence thermal fluctuations, even at room temperature in nanoscale systems. The implications range from fundamental questions about the quantum classical boundary to practical applications in quantum thermometry and energy harvesting. This remains one of the most active and exciting areas of research in nanoscale physics, with new discoveries happening regularly.